Hi, my name is Bill Fortney and welcome back. In this video, we're going to be looking at how do you tell data set A is different from data set B by putting a confidence interval on the mean. So where are we? We have something we're interested in. We've designed our experiment. We've checked for validity. We've explored the data. So we use this to design our experiment. Here's the process that we use to check our data. And now we're going through this process and we're right here in the middle trying to decide whether two sets of data are different or not. And we saw tool number one is we just compare the graphs, knowing what to expect from those. And we found that this tool only works when it's a no-brainer, when there's either a clear difference or clear not difference. But when they're close, there's overlap, we needed another tool. That second tool is we're going to create a confidence interval on the average and add error bars on our graph, and then we'll be able to see whether these bars overlap or don't overlap. Okay, so what we've always done before is we've looked at these graphs and we've compared them. But how are we knowing what we should expect when we look between the two? And you remember, it's following a normal distribution. We've had to assume that when we're looking at the individual values, that it's roughly following a normal. And so then we know what to expect. So we've kind of gone up and down 2 or 3 standard deviations and said, okay, if these boxes are outside of that, then no, it wasn't random. If they're overlapping, that's where we said, it's a little, we're not quite sure. Well, what we're going to do now is we're going to take the average of our 2 data sets or 3 data sets or however many, or however many we have. And so the question now is going to come, okay, well, what can I expect from my averages? And let me help you see what you can expect. It's actually pretty cool. So before, we knew, okay, if it was normal, we knew what to expect. And you remember we plotted 1,000 volts. We said, look, let's assume we have full knowledge of our population, which we never do. And we kept plotting volts, and it's going to look like this. It's going to fall within, most are going to fall within 1 standard deviation, some 2, and a few out there like that. Okay, now let's say we come in and we take a sample of 20. We get an average of 81.22, standard deviation of 1.08. Okay, now, if I take another example, do you expect the average and the standard deviation to be exactly the same? And I'm pretty sure you're going to say, well, no. I mean, it's varying. You're going to catch it a little different. And yes, you are. So we did it, and it's 80.95 and 1.05. I mean, they're close. Okay, how about if I take another sample? Same thing. They're going to be a little bit different. So our averages are varying. Well, how are they varying? Our averages are random variables, just like our individual values. And what that means is they're going to have a shape, they're going to have a central tendency, and they're going to have a spread. So the shape of the averages is going to be normal, always. It doesn't matter what the population was. We're not going to have to assume normality. Averages are distributed normally. And I'm going to show you the central limit theorem in a minute and show you why I'm so confident that that's true. But the averages are normal. Well, the average of them is the same average as our population. The standard deviation of the averages is the standard deviation of our population divided by the square root of how many samples we have. Shape, central tendency, spread. We know about the distribution of the averages. So we know what to expect for an average of 20. We can do x bar plus or minus k sigma of x bar, just like we did up here. In our case, 1 over square root of 20 is 0.223. So we now know an average of 81, or we could take these 3 and average them together and say, okay, that is our estimation of the population standard deviation. Again, if we didn't know for real, we would average these 3 and say that's our estimation of the population. These 3, the population average, these 3 are estimate of the population standard deviation, divide by square root of 20. That's our estimate of the average standard deviation. Pretty cool. So now, distribution of the average of 20 bolts from our factory, what's it going to look like? And hopefully you're going to say, well, it's going to look like just like this, but these numbers are going to be different. This top number is going to be 81 plus 0.233 times 3. And lo and behold, that's exactly what it is. They're normally distributed just like this. It's just a much narrower band. Well, why a narrow band? Well, because the standard deviation is the population divided by square root of how many samples we have. There's going to be a lot less variation in the average, okay? So just let that sink in for a second. The averages that we're taking are random variables, and we know what to expect out of them because their shape is always going to be normal. So the same thing, we can use the average that we calculate as the estimate of our population. We can use the standard deviation, the estimate of our population. Then we can divide it to get the estimation of our average distribution. So now we have two things. We have one, the probability of getting individual values, which is what we've been using all along. But with that, you have to assume the population is normal. We've said that all along, that you have to assume it's normal. Even if it's not normal, we might be in the ballpark, but you have to assume it's normal for this to be completely true. Now we have confidence intervals on the average of n values. N is our sample size. And for these, we don't have to assume they're normal. They both give us an idea of what to expect. The difference is up here, it's telling us what we can expect from individual values, what kind of range. So if one part is below, I go to jail, I'm interested in up here. Down here, it gives us what we can expect from an average of a certain number of values. And we're going to see this is really, really important. This is one of the core ideas that's used in statistical process control, where companies monitor their process. They know when they're producing bad by studying and looking at that average and what happens. Okay, now one thing I want to highlight. What's the difference between this and this? I didn't call this a confidence interval. It's not. It's the probability of getting these individual values. Down here, this is a confidence interval. That's a statistical term, and it's easy to think of a confidence interval from a practical standpoint. Let's say this is my 95% confidence interval. Then I'm 95% sure the true average falls within there. Statistically speaking, here's what a confidence interval means. A 95% confidence interval. If I calculate a confidence interval on 100 averages, so I get an average 100 different times, I calculated a confidence interval, 95 of those intervals will contain the true population. Now, practically speaking, the way people use confidence intervals is they say, okay, this one that I calculated, I'm 95% sure my true value falls within there. But from a purest statistical standpoint, that's not exactly what a confidence interval is saying. But that is how it is typically interpreted when you're doing real world statistics with it. Okay, so now we know what to expect from averages. Remember I told you I would tell you about the central limit theorem. Here's what you're seeing here. This is the population distribution. So say we have a uniform distribution. We have kind of a crazy distribution, and we have something that almost looks like an F. What this is down here is this is the distribution of the averages if we have a sample sizes of 5. And look at this. All of these look approximately normal. You're saying like, well, that's not normal. I mean, it is. It's symmetric. Even this crazy one's pretty symmetric. Look down here, if I take 30 samples, all of those look normal. So here's what that's telling us. It's showing the proof that no matter what the population distribution, the averages are going to be normally distributed. Even if you have only 5, estimating what's happening with the averages with a normal distribution, you're not going to go way wrong, okay? That is the beauty and why we like to go and work with averages when we're trying to determine a difference because we don't have to assume that the population is normal. Okay, so how are we going to do this? We looked at 201. There was overlap. You know, it was hard to tell. So we've calculated our averages. So look what we have. Here's the average, our sample standard deviation. Notice I have S of X. That's standard deviation of the individuals. I have 10 points. Now notice I have S of X bar. That's S of X divided by square root of 10. And then I have T times that. My T right here is 3. I'm going to explain in the next video what I mean by T. That's the K value that we've been using, okay? And so I'm going to put that on here as error bars, and that's what those are. So how did I get this top one? Okay, I said 49,951.6 plus 3 times the standard deviation of X bar. I did the same thing on the lower one. Okay, how about over here? I said 48,987.3 plus 3 times the standard deviation of 179.8. And now what is this telling me? This is telling me that I've got 3 standard deviations. Look, the real average is going to be in this range right here. My average could vary anywhere in here, and my average could vary anywhere in here. Even if my average is the true one was way down here and way up here, these guys still don't overlap. Yeah, I'm sure that did not happen randomly. There's a special cause. That's what we're doing with the averages. Now, let me show you the difference. This graph is really messy, but I want to show you the difference. What we've done before is we've taken the standard deviation of the x's, and we've said, look, let's multiply that by 2 or 3, put a box on here, and then compare these two. So that's what what tool number 1 is saying. Is it's saying, look, think of a confidence interval on their individual values. There's not heat treated. Here's heat treated. Okay, if it was bouncing around doing this, would you expect it to do this? No, it's outside of what we would expect from our confidence interval on individuals. What we're doing with tool number 2 is we're saying we're also going to calculate the standard deviation of averages and multiply that by 2 or 3 or whatever we're doing. Confidence intervals on the averages. And so now we're going to compare averages using the standard deviation of the averages. We compare individuals with the standard deviation of individuals. That's what I wanted you to see. We're using 2 different standard deviations. Up here, I'm using 532. That's this guy. Down here, I'm using 168.4. Okay? That's what we're doing. And let me just show you a couple more examples. Okay, notice one here. It's a no-brainer. There was a special cause. And look at our averages. There's a huge difference there. Some people like to show this and this. Some people like to show this and the averages. Some people like to show all 3 when they're telling their story. That's going to be part of what you're going to deal with, is when you get your results to present them to somebody, which one do you think communicates better? Okay, here's another one. You see, now we got a little bit of overlap, but you come down and look at the averages and they really don't overlap. So this would be a case where it was unclear here. To the averages, to me, there is a special cause. These averages could vary anywhere in here. They don't overlap. No, that's a special cause. Heat treating mattered. Okay, now we get to this one. And you see there's a good bit of overlap. Now my averages start to overlap. Well, how much overlap's okay? That's where I need another tool. And then let me show you one more example. You remember the glue? I said we were trying to find what kind of glue. And I'd shown you this graph. Let me show you that graph with the averages and the error bars. Here it is right here. So it's a no-brainer from here to here that those are the same. You see that right here. No-brainer there. And you can't tell from here to here. Well, you can't tell with the error bars either. We need another tool. And that tool is going to be a t-test on averages, and then that will be the final video. And how do you tell the difference between set A and set B?